Hi everybody, welcome to our next project. Yep, we have a couple of brothers here. It's a pair of Scott vintage, probably 1960s. We'll look up the model numbers and when they were manufactured. One is a stereo receiver and the other one is just a stereo integrated amplifier. And these are going to be some fun projects to restore. I had either this model or a very similar model to this a long time ago, and it sounded amazing. I was surprised how good this thing sounded. And this one here is going to be interesting because it actually was a kit. So I've never taken either of these apart. I've not plugged them in. I've not tried them. I have no idea what kind of condition they're in. This receiver, this model 382B, definitely needs some work done on the cabinet. It's kind of scuffed up and old, so this will have to go down to the wood shop and get restored. This one, the cabinet's in much better shape, and well, we'll have to see what kind of condition they're both in. This is a Stereo Master LK60B, and again it says Scott kit. I believe this was a kit that was assembled, and this of course was a factory made receiver here. And the Stereo Masters from this era, there were several. There's like a 340. I think I had a 342 was the one I had. This is the 382, and the main difference is I think the 342, the one I had, was FM only. This one is FM and AM, so it has both of the broadcast bands. So it should be a really interesting project to do these. I'm going to do the receiver first. I'm going to save this one for last because I think it's going to be fun. Anything that started out its life as a kit is always kind of a, kind of a mystery to unlock, what people did and what kind of work they did and if it worked at all. I'm sure it did. Maybe not, though. We've had other things in the past that never worked right. So that's it. Stay tuned, and we're going to get this one off the bench, and we're going to start on this one. Okay, we got this up on the Lazy Susan here, and it's pretty cruddy. I mean, you can see all the dirt on these knobs, but this will all clean up. I don't see any bad scratches or anything, but I do see some of the plating is kind of worn off of the brights and so forth, but that's not a big deal. I don't really care about that. You can see here that the finish is just about worn off of this wooden top. And of course it's veneered plywood. And you can see this aluminum plate that goes in there. And I think this was actually brass plated at one time as well. If I recall correctly, that's what color those are. This case was an option. They didn't all come with this, I don't think. The one, my 342, did not have a wooden cover. It just had the interior case, and you'll see that when we take it out. You can see how dirty this thing is. It's kind of cool. All of these Scotts from this era, they didn't really have much in the line of heat sinks on them. They had TO3 output transistors, which is what's behind these four covers, but they just uses the back of the chassis as the heat sink. And the power transformer is also attached to the back of the cover, and it kind of sticks out the back like that. I do believe that there was an AM bar antenna on here, which is missing, so we'll have to come up with something for that. Of course, all the inputs are real dirty and tarnished. Your speaker terminals and speaker fuses, your antenna. There's not much to this. Pretty simple design, and your ubiquitous dirt, It's not a Tony video unless there's dirt and crud in there. But that's the way we like them, huh? All right, let's slide this out of the case because the feet are missing and the screws that holds the case onto the chassis are also missing. So this will just slide right out. Okay, and we can see with the cover off, we need to do some dusting before we go any further. So I'm going to get the vacuum out and I'll save you all the noise, and I'll come back once we get this swept off a little bit. Okay, that's much better. So let's take a look at the fuses. That'll be the first thing that tells us what's going on here. This is supposed to be a 1 1/4 amp slow blow, and that definitely looks like a slow blow there. And this is a 1 1/4 amp fuse. Can you see it? Yeah, there it is. 1 1/4 amp. Okay, so that one's good. So far, that looks pretty good. And these are supposed to be AGX 2 amp. Okay. See, those are shorter than, those are probably a little bit shorter than an AGC fuse. Maybe not. Yes, they are. So you can see an AGX fuse is shorter than an AGC. So that's an oddball fuse. And that certainly doesn't look like 2 amp to me. It looks like I could power my house off of that fuse. What is that? Holy crap. That is a 14 amp fuse they put in there. Okay. What's this one? The same thing. 32 volt. 14 amp. Wow. Did you hear Bella? She doesn't even think this is right. You tell them, Bella. So I'm not going to plug this in, obviously. But I will take this top cover off. You can see the ones that have the wooden cases don't have the full metal covers all the way around. My 342 had the metal cover that wrapped around because it didn't have the wooden case on it. So all we got to do is take this top off. So let me get these screws out and we'll be right back. Okay, we have the camera moved up a little bit. Screws are out. Let's open this up. Okay. Put this cover down. And the inside's just as dirty as the outside. Okay. Yeah, this is old school circuit boards here. You can see. But they're very nice. They actually look in pretty good shape, and it doesn't look like anybody's really worked on this side very much. But, of course, that's famous last words. We've learned that from other videos, haven't we? And these transistors here are all up on sockets, which is pretty cool. I remember that on that other one. That was about 30 years ago, though. I got rid of that other one. I actually didn't get rid of it. I left it somewhere, and then I never came back and got it. So, okay. Well, let's flip it over and take the other side off and take a look at it. Okay, let's get these last two screws out here. Let's see what we have. Okay. Well, those covers do a good job of protecting the innards, don't they? Wow, look at that. What a cool receiver. Nice. All the original parts, it looks like. And now you can see the filter capacitors in there. And yeah, they didn't put very big filter caps for this amp, but of course I don't think this thing was very high wattage. This thing's probably 30 watts per channel, something like that. We'll look all that up. We'll get a spec sheet out. But we have our rectifiers right here. And this might be, well, yeah, this might just be a single rail power supply. And of course then that would mean these capacitors would be your output coupling capacitors. Which I think that's what this was. I forget. So this wasn't a normal, it was a single rail power supply. So it had a floating center point. It was above ground. So you had to have that isolation capacitor. But we'll look at that in the schematics here in a little bit. I'll show you what I'm talking about. You've seen these before. I've showed them to you and explained it in other videos. Okay, so yeah, one lonely little power supply cap, and there it is, and it's, wonder what it's rated at. Let's get a flashlight in there. See what we have. 1,000 microfarads at 35 volts. That's it. There's your filter. Okay. Fair enough. And then here's your tone control section. The tuner was on the other side. It's a very simple receiver. And everything's on sockets, at least for the transistors. And we'll check some of these caps out and see what kind of condition they're in. I have a feeling some of them are going to be bad, and some of them are probably going to still be okay. We'll see. But we'll go through all that. First thing we want to do, though, is check these transistors. When there's 14 amp fuses and you have a a capacitor coupled output, why would you be blowing fuses? And why would you need to put such large ones in there like that? It doesn't make a whole lot of sense. So we'll look at the transistors, we'll get some schematics out, and we'll go from there. All right, check it out. Those look like original 2N3055 NPN transistors. These were very, very common TO3 transistors. The 2N3055. They're so popular they actually have I think they have their own Wikipedia page, if I'm not mistaken. But these things you could buy them at Radio Shack. They were very, very common. They were used in many different types of electronics. They were one of the earliest high-powered silicon NPN transistors. And the earliest ones, which these ones may be, had a much lower transition frequency than the later models that you would buy today. But anyway, really interesting stuff. So these are original, and maybe they're still good. We'll pull them out and check them real quick. Okay, do you all remember how to check a transistor? I showed this in several videos. So this red lead is our P, or our positive lead, and the black lead is our N, or our negative lead. And this is supposed to be an NPN transistor, but if we didn't know that, we could figure that out. And with a TO3 transistor, if you look at it, if you notice, there's a short distance from this hole to this hole, and then there's a long distance from here to here. So this one's longer, this one's shorter. If you hold it with the short side down, okay, on the right-hand side, this is going to be your base, this is going to be the emitter, and this is going to be the collector. So if we remember, this is supposed to be NPN, so the P lead should be on the base. And if I go to from the emitter to the base, I should see a voltage drop of, a diode drop. And if I go from the collector to the base, because the collector is the case of the transistor on a TO3, I should see that. And if I go from collector to emitter in either way, I should get nothing. And if I swap the leads around, I should not get anything with that. So again, your base is always the center, so you have N, P, N. So, and if this were a PNP, you'd swap them around. So I show this on a video. So this one is good, as we can see. So we have one good transistor. We'll put this one back. Let's get the next one out. Okay, we're all used to these cheap component testers, and everybody has one. They're inexpensive. You can buy them online. And you can connect the transistor up any way to these three leads, and this will tell you the pin out of the device, and it'll tell you if it's good or bad and so forth. But before these things, we had devices like this. This is a Sencor Cricket, and there's a couple different ones. This is the old model, the TF26. There's a later one called it the Super Cricket, which I don't have. Maybe I have one, I don't know, but I have this one. Anyway, so we turn this thing on, and you take the leads, and you can connect them to the transistor in any way you want. So we'll just grab any three here. And we turn it down to gain. And we select NPN or PNP, and even if you have it selected wrong, it doesn't matter, it just won't test. So for instance, we set this to PNP, and then you just push the buttons. And of course we get no response. So now we switch it to NPN, and you hear that tone, and two of the buttons should read something. So there's your gain. Your gain's pretty high. Gain is a good or bad thing. It doesn't tell you how much gain the transistor has. It's just a good or bad, kind of like an emissions tube tester. So since it's in the green, it's good. Now these numbers are for leakage. So to test for leakage, we slide this up to leakage, and the same buttons that tested the transistor good, we push those buttons again. And if there's any leakage at all in microamps, it'll read how many microamps of leakage the transistor has. So some of the germanium transistors will show a little bit of leakage. Just that's how they are. And the cool thing about this is this tester will actually test a transistor in circuit, so you don't have to remove it. And it's just a good or bad test, so it doesn't tell you things like gain. It doesn't tell you nearly the amount of information. You don't know VBE, you really don't even know the pin out of the transistor, but you do know if it's good or bad. So it's good. And again, I can connect this to the transistor while it is installed. Let's see if we can do that here. Okay, I just randomly connected those three leads to a random transistor in there. And it doesn't matter if it's a FET, a field effect transistor, or just a BJT, a bipolar junction transistor. And once again, put in gain. And it can read in one or two of the buttons. You could see the one button has a little different sound than the other. That's normal, but that's more than likely going to be a good transistor, and I checked it without even removing it from the circuit. Now this thing isn't perfect, but you can actually use it to troubleshoot transistors as long as there's no power being applied to the circuit, obviously, and it'll check transistors and FETs that way. And then you can go check for leakage, and you're going to see some leakage right now because you're checking in circuit. So that's to be expected. But again, quick test without having to remove components. We like that. Okay, now I have this hooked back up to this transistor, and I have the leads connected differently. And you can see, and that's good. But what happens if, for instance, one of the leads was open on a transistor? So we have an open, and you can see it will not test good. And also, let's say we have a short. Let's say we have an emitter to collector short. Let's call it that. So I'm going to put a jumper between the emitter and collector, and we're going to simulate a short circuit. And you can see it doesn't work. And if you go to leakage, you're going to peg the meter on like 4 of the buttons. So that's a quick way to test if you have a faulty transistor. And that's what a faulty transistor would look like. So I'm not telling you to run out and go on eBay or something and buy one of these. These are kind of novel things. And of course, with these new, test everything component testers, these are really, really good. And a fraction of the cost of what you'd probably pay for this, because it's obviously a vintage piece of test equipment. But these are cool, and the in-circuit testing with them actually is a pretty cool thing. It's not perfect, doesn't work all the time, but it can actually save you some time, especially with older gear like this. So I just thought I'd show that to you. It's just a kind of a show and tell thing. Okay, so I've done a little bit of housekeeping and kind of cleaned it, and really all it was loose dust. There's no dirt in this. It's pretty clean on the inside. And the way I printed out the service manual on this, and on the big picture they kind of have a block diagram, but they don't show the circuits of on the boards, but they show all the external components like the power transformer and the power supply, and then they show the actual board. And then if you want to see the circuitry of each board, then you have to go to the individual pages, which we have. So the first thing we want to do is, I have it connected to the dim bulb tester, and I only have, I think, a 40 or 60 watt bulb connected for current limiting, and that will at least see if we have any shorts. Now we know the output transistors are good, and so we'll just check our power supply and see what happens. So make sure we don't have a shorted capacitor. So let's look at the dim bulb, and we'll turn the power on. Where is it here? Okay, that was just tiny little voltage there. Not much current, or tiny little current I should say, but you can see it's lit up. So there is power in here. I have a feeling that capacitor is almost open. I don't know. But let's look at our 50 volts. And the 50 volts is right here, so it's the top of that capacitor, and where it comes out of these two diodes. And you can see that right here. So here's the two diodes where they join. Here's the two inputs. So let's see here. See if I can check on the stud of this diode. And yeah, you can just barely see, if I roll down here on the camera a little bit, we have 48 volts, and that would be, I would expect that on our 50 volt power supply, because we have that dim bulb in there. So there can be a little bit of a voltage drop. The 12 volt source is going to be up here on this board, and we have a 12 volt and a 25 volt source. And let's see, the emitter of the transistor, I think that's right here. That's where, I'm sorry, the collector is where your 50 volts goes in, and then the emitter, I'll check it over here, 27 volts, so it's a little bit high. And that's even with that dim bulb, so it might be because there's no loading on it at all right now, or it's very not heavily loaded because of that current limiting. And our 12 volt source should be up here somewhere. Take a look at it. Let's see if this is it. And our 12 volts right now is 13.2. So it's a little bit high also. And looking at the circuit, they're using a 12 volt Zener right here. So, and that would be this little diode up here. Let me see if I can get back a little more. So if we check the two sides of this diode, that's the low side. See if we can get on the high side, and there's 13.8. So even right here, the top of this diode is 13.8. So this diode's a little bit high, it's reading right now. So if you really wanted to make that perfect, we would want to replace that with a proper 12 volt Zener diode. And that would limit our voltage to 12. So bottom line is the amplifier, or I mean the power supplies are functioning, and there's nothing too dangerous in there. Now if we go to millivolts AC and we go back to our 48 volt supply, that's not bad. 162 millivolts. So about 160 some millivolts of ripple, which tells me the capacitor is still working. So that 1000 microfarad capacitor in there is good, or at least mostly good. Now, of course, it probably will sag once you put a heavy load on it, but it's good enough to keep the ripple off at idle. Okay, one last thing I want to check before we put a set of speakers on this and see if there's any sound coming out of the amplifier, is I want to check these coupling capacitors. And what do I mean by that? Well, here is your output, those four 2N3055 transistors, and you can see they actually are sitting at about half of your rail voltage. So I bet if you measured here, you would probably see somewhere close to 24 volts if you have 48 volts going in, and or down here, so about half of the voltage. So what that means is this capacitor is the only thing isolating that DC from your speaker terminals, which are down here. So we want to make sure that this capacitor is not shorted and not severely leaking. If they're good, we don't really care about the bias or anything here. The speakers will be safe. And then we can connect some speakers just to see if there's any sound. So let's check those real quick. Okay, we have our handy dandy capacitor wizard. Help me, Mr. Wizard. That's good. How about that? At least as far as ESR is concerned. Very good. All right. Okay, we have some speakers connected, and things plugged in. It's still on the dim bulb tester. Let's turn this thing on and see if we get it. Now, understand, this is a capacitor coupled amplifier, and as such, it has a DC offset on the center of these two transistors. And what's going to happen is when you first apply power to the amplifier, that voltage is going to want to charge this capacitor through your speakers, because there's a path from here to ground through your speaker. So that's why these amplifiers, if they don't have a relay on them, you'll hear a pop when you turn the amplifier on, and that pop is the speakers actually seeing that voltage for a split second while the capacitor charges up. Now once the voltage here and here are at the same potential because the capacitor is charged up, the speakers will be quiet and there will be no signal from here to ground anymore because this cap is now charged, if that makes sense to you. All right, flame on. And I'm going to hold the microphone near the speaker, and I'm going to see so we can hear what it sounds like. Here we go. Okay, that wasn't a very loud pop, but it was there. But I do hear this. I don't know if you heard that. If you have headphones on, you probably can, or if you turn the volume up on your speakers. So that was both channels. I just moved between the two channels. You can hear both of them have a pretty good amount of hiss in the background. So that is probably either because of a bad capacitor or a leaky transistor. So and both channels are doing it, so it's something. It could be a common problem, which would be a capacitor or something. But that's something we'll have to look into down the road here. But it does seem to work. So let's see if we can feed some music into it. Okay, we have some YouTube safe music queued up. I am going to try a song here called Sunshine Samba, whatever that is. All right, here we go. Let's start it up and let's turn up the volume. That was weird. Oh, never mind. The reason that was doing that is I forgot I had the dim bulb on there. Let's switch in a bigger bulb. There. That might be some of our hiss too. Actually doesn't sound bad, other than that little bit of background hiss. But the amplifier sounds really good, both channels, and we're getting good stereo separation. And I've not cleaned any of the controls, but none of them seem to be scratchy or anything either. So in general, this thing works. Okay, we now have an antenna connected to the FM, and I have it set to FM. And you can see and the tuner works. Other than that little bit of background hiss when you're at 0 volume, this thing works perfectly, and it's got incredible bass, very solid. I did look real quick at the ESR on the power supply, and only this capacitor back in here, let me see here, just this one right here is bad. It's totally, I mean, almost totally open. Real high ESR. But other than that, everything looks good. So, a bunch of lights are out. It sounds like I'm getting stereo reception. But I noticed the meter is not working at all, and we're not getting the stereo indicator light. So, I'm going to grab a couple of bulbs and pop in there and just see if it's just the bulbs. Okay, all the lights are replaced and we're still not getting a stereo indicator. And I can tune right in on it. And when I go to left and left plus right, I get that. Left minus right, I'm getting nothing. Right only and left only, but it's playing in mono. So that tells me that the multiplex circuit isn't working. So we'll have to work on that. This meter doesn't work at all. I don't know if the meter is defective or if we actually just something's not working with the circuit that drives it. But that's tuner stuff. We'll look at that later. Turning to AM. Yep, I'm getting AM. So there's no antenna on it. It needs that loop stick antenna. And we'll either have to make one or something. We'll figure out. So, amplifier works good. I checked all the capacitors on here, and from an ESR standpoint, every capacitor is good in this amplifier, in this whole receiver, with the exception of that one up on the power supply. Every electrolytic. As far as ESR, now we don't know if any of them have any leakage, or if they're the right capacitance, but judging by how everything's working, I don't think any of them are bad, just in all honesty. So we may not have to mess with that for now, anyway. So we may come back and do a recap another day, but really the only things we have to address in this receiver is going to be the multiplex, and we'll change that one capacitor. And then we'll go through and we'll do the bias setting. And this receiver is pretty much ready. Okay, so I have not touched this thing in a week or so because work has been that insane, and I'm just now getting some time to be on the bench again. And where we left off, we were looking at the FM multiplex and the tuner section of this, and we had also determined that the amplifier itself had this background hiss, and I'll put the microphone next to the speaker again. You can hear that, and although if there's ambient noise in the in the room, you don't really hear the hiss a whole lot. If you're in a quiet room, it's very annoying, and it shouldn't be there. It should be quiet. So a couple things we're going to look at. I want to deal with that noise first because it's kind of hard to repair the tuner because you can't really tell if you're looking at the receiver, how much of that is the background hiss of the amplifier and how much is the actual tuner section. So we're going to take some time here and try to repair the hiss problem in the amplifier first, and then we'll go back to the receiver, or the tuner. Now, a couple things that we've found, and that is the hiss is in both channels, and it's equal in both channels. So it's probably not a leaky transistor in the amplifier section somewhere. It has the same hiss no matter what input you select. So you can select auxiliary, you could select tuner, phono, whatever. It's that same hiss. So it's something common to both channels, and it's something that is not related to the inputs. So the only thing I can think of in this simple design of a receiver that's common to everything is, of course, the power supply, which is down here. And this little power supply board, we can break that down on here, and you can see it is relatively simple. There's 3 transistors. There are 2 that are on that little tiny circuit board, and a third one that's a pass transistor, and it's a big TO3, and it's mounted to the chassis. And right here is where you're coming in with your 50 volts. We're going to look at all this. You can see it down here at the bottom going in. And then you have a 12 volt and a 25 volt output from this power supply. And what we want to see is if that noise can be traced there. Now I'm going to do something a little bit different. When you're looking at very, like at high frequency hiss that's in the audio spectrum, and it's possibly very low level, carrying on a DC, DC offset because it's a power supply, it's hard to look at it on an oscilloscope because the probes themselves will pick up some noise when they're around, they'll couple to the receiver, and you really can't tell if that noise is the noise you're looking for or if it's noise being generated by the probe of your scope. So we have to think of a little more novel approach to this. So what we're going to use is I'm going to use my little 147A signal tracer, and you don't have to have one of these. You can actually use a audio amplifier, like a little high gain amp, or even a little guitar amp, one of those little tabletop ones. The main thing is the amplifier has to be very quiet. If you short the input together and you turn the volume all the way up, the amplifier should be very quiet. So I'll show you an example of that. I'm going into the audio input. The audio input has a capacitor in series with the input. That's extremely important because where we're going to be putting this probe is going to have DC levels on it, up to 50 volts in this case. And you certainly don't want 50 volts DC going into this little amplifier. So knowing that this has that capacitor coupling in it, it's safe to do that. If you're going to use a guitar amplifier or some kind of external amp like that, make sure you put a capacitor in series with your probe so you don't let that DC go into your amplifier and cause damage possibly. Now the first thing we want to do is, if you notice out in the open, you can hear, I'll hold the microphone, you can hear it's kind of noisy, right? It's noisy. But if we ground the probe, you can see I just grounded it, I can turn the volume all the way up and there's no hiss whatsoever. So this is a very quiet amplifier. That's important because we want to compare what the noise is in the amplifier and the noise in what we're testing. So the first place we're going to test, and I'll see if I can get this whole thing in view. Let's see. Is we're going to test this input where the 50 volts is coming off of the power supply, and you got to kind of jump back and forth. So you can see here's your rectifiers, here's your 50 volts, there it goes into there. I'm going to check that, and that is actually going to be right up here on the collector of this big transistor here. And that's the pass transistor that's not on the board itself. All right, so we're actually looking at the collector of this transistor right here, and you can see it. Okay, so it's hooked up. Let's listen to what it sounds like. All right, so you hear that sound? That's your 120 hertz hum from your rectified, unregulated power supply, and that's normal because there's always going to be a little bit of ripple on this area because the only thing you have is this capacitor. And a lot of you will say, can I put a bigger capacitor in there? Everybody wants to put massive 80 billion microfarad capacitors on here thinking it's going to make their amp sound better. No, it will make absolutely no difference. I did the math on multiple videos showing you that this will make very little difference. Perhaps when you're talking about dynamic power, you can have a small improvement. We've shown that. But if the transformer and the capacitor are properly matched with how much energy the transformer can provide maximum and how much the capacitor can store, adding capacitance will not make much, if any, difference. So let's get that out of our system. This cap is not bad. It is a good capacitor, so that little tiny bit of hum is normal. Now the first place we're going to look at here is right here where it goes into the base of that pass transistor. So that's right here. And this is part of where you're going to get your regulated 12 and 25 volts out of. And you can see there is a 12 volt Zener diode, and we already determined that this diode is reading high. It's reading like almost 14 volts. It's 13 point some volts. We also determined that this capacitor here at the end is bad, but this one here is okay. So this 30 microfarad is, or 50, whatever it is okay, but this 10 microfarad is not. And you notice they're both on the same line, but they're not in parallel with one another. This one goes directly to ground. This one does not. It goes through this resistor and to ground through a 10K. So anyway, we're going to check here, and then we're going to check the emitter. So we're going to check the base and emitter of the pass transistor and see if that hiss is there. So first things first, we're going to go on the base, and that's right here. And then we're going to go down and turn our volume up. Did you hear that? Now let's just compare it to when we ground the probe. Okay, so I've just grounded the probe. Notice there's no hum or no hiss. So there is hiss right here. Let's go over to the emitter of the transistor and see what we have there. Okay, we're now connected to the emitter. I'll take my microphone off again. and we have that hiss there. Now I don't know if this hiss is what's causing all of this, but it's definitely there, and it sounds suspiciously the same frequency as what is on the speaker, which is right here. So I'm inclined to think that part of this noise is coming from our power supply. And that can be possibly a noisy transistor or something going on with that Zener diode or something like that. So the first thing I'm going to do is I'm going to rebuild this power supply. I'm going to replace these transistors because they're inexpensive. I'm not going to replace the pass transistor because I don't think it's bad. And I'm going to replace this Zener diode, and I will change the couple of electrolytics, although the only one that really tested bad is here. But remember, a ESR meter only checks for equivalent series resistance. It does not check for leakage. So the capacitor could have some leakage, which could be causing some of that noise as well. So anyway, for what they cost, we're going to redo this little board, and then we're going to see if we made any improvement. Okay, all the components are replaced, rebuilt, and here's the verdict. These two capacitors were bad. This one was really bad. It had really high ESR, like 22, 23 ohms. And they both read really high capacitance, like 50% high. These capacitors read perfect, and they still could be used. This resistor is in perfect condition. It's a 270 ohm, but it's reading a little bit high. It's reading 290. That would still probably be okay, but just in case, since this is a carbon comp resistor, I replaced it with a metal film of the same value, and it is exactly 270 ohms. You can see it back there. And I think the biggest culprit of all was this Zener diode. As soon as I touched it, it cracked in half. So I think it had seen better days, so it's been replaced with a brand new one. And the pass transistor, I left it alone. I think it's fine. Turn the amplifier on. And there is no noise. I'm holding the microphone next to the speaker. Our hiss is totally gone. So that noise was coming from the power supply. Let's do some quick spot checks and make sure our voltages are good. Let's see. Okay. There's your 24 volts. It's 23.6 or 25, I think, whatever they call it. There's your 50 volts. And then your 12 volts is down here. It's a little bit low. It's 11 volts, 11.1. But that's okay. It's not going to hurt anything. It should work just fine. And if we go through and do our signal tracer just to see if that was what helped us to determine this problem. We're connected back onto the emitter. And if I go down here, no noise at all. All the noise is gone. So you can see how you can use this signal tracer or an amplifier to troubleshoot noise in a power supply. And in my opinion, it works. In some cases, it works better than an oscilloscope. When you're dealing with, you're not dealing with hum, but you're dealing more with a hissing sound or a high-pitched, hissing type thing, high frequency. It's very hard to see that on an oscilloscope because an oscilloscope will have so much, at that, it's very low level. Remember, you're talking millivolts. When you're looking at little millivolt signals like that at high frequencies, your scope can't always discern that unless you have your probes really well grounded and shielded and so forth. Or your scope probe will actually couple with other things in the receiver and you'll get fake noise that's not real. So that's why I like this method. But there's an idea how to check a power supply. Okay, now it's time to look at the FM stereo problem. We know that the AM works, and we know that FM mono works, and it tunes in just fine. And right now I have a 98 megahertz carrier frequency, FM, with no modulation. Excuse me. And if you turn it up, I can tune on and off of it. And it tunes in real well. But I do not get, when I turn on a pilot signal, I do not get any stereo indication whatsoever. So the first thing we want to do is kind of identify where does that all take place in the circuit. When you look, the multiplex circuit that we have here does not match the multiplex circuit in the instructions. And I actually went through and I did an exhaustive search of H.H. Scott's service manuals, and none of the 342 or 382 series receivers at any time ever showed this multiplex board. It's different. Now, it is in fact an MX14 board. They call this the automatic multiplex demodulator, MX14, and on the back of the board it says that. But you can see it has very different looking, at least the little cans here, the tuning cans, are different than the ones here. See how these are large? These are the old aluminum style, like what you see down here on the front end module. They're supposed to look like that, but they don't. Fortunately, the circuitry is identical. The only thing they did was they moved a couple things around. These transformers are still the same coils. They're just the small outline ones, you know, the smaller Japanese style ones. And this resistor network that goes to your output for your stereo separation and everything, on this particular module, they're standing up on this little board here. Whereas on this one, they're lined up in a row, and I can kind of show you that there. You can see how these, and they're all 10K resistors, and they're just lined up. In other words, instead of these resistors standing up, they're laying down. Got somewhere along the line, must have changed their source for components, and they just kind of modified their board to accommodate that. The other thing I noticed was it said Japan down there, and I don't think the H.H. Scott receivers from this era were made in Japan, but I could be completely wrong on that. And if any of you know better than me, please let me know down in the comments. That would be cool to know. Okay, we're going to do something a little bit different. It's not something you have to do, but it's just something cool that you can, I don't know, just that it'd be fun to look at. Some of you may have not ever seen this before, but what we're going to do is we're going to look at the output of the stereo. Of course, I have a mono microphone on here, so you can't tell if there's stereo separation, but I can. I can go between left and right, and the sound goes from the left to the right speaker, and there is separation. So if I turn it on, I go to left, I go to right. It's not perfect, but I have separation. So let me turn the volume off, and what I'm going to do is I'm going to connect my oscilloscope, like we normally do, to the record out jacks of the receiver. Now this is something we do all the time, and then you connect channel 1 to the left and channel 2 to the right, and you go into dual channel mode, and you can look at the signals individually. But you can also do the same thing. You can connect to channel 1 and channel 2, and you can put your scope into X and Y mode. And if we do that, let me move the camera. So this is how we normally set it up. We have left channel going into channel 1 and the right channel going into channel 2. We have them split, and you can see the right and left. And if I go to left and right, you can see the separation. You can see one side has more separation than the other. So the right is actually, you have better separation than when you're doing left only. If we go back to stereo, If I move this back to single channel, and then I move my knob to differential, or to XY mode, you can see that you get a slanted line when you have stereo. When you have a mono signal, you can see it gets a higher amplitude. And you don't see that little carrier on there of that 19. See, the 19 kilohertz isn't 100% filtered out. These old multiplex circuits are known to do that. That's normal. So you see there's your 19 kilohertz, and you can see as it kind of fades in. All right. Now watch what happens when I go to right and left. This is left minus right, left plus right. So left plus right and normal stereo are the same. This is how it should be. If I go to left minus right, you can see it's out of phase by 180 degrees. So you have, it's shifted. Or by 90 degrees, I'm sorry. And then if I go to right only, the line goes straight up and down. It's vertical. And if I go to left only, it should be totally horizontal. And you can see it is not totally horizontal. And that is because that's the channel that doesn't have quite as good separation. So if you had it perfect separation, you would have a horizontal line. So left only, right only, left minus right, left plus right, normal stereo, and then take the carrier away, mono FM. Pretty cool. It's just a quick way that you can check in XY mode your stereo separation, and maybe we'll try to do the alignment with this and then go back to looking at the two channels individually to see if it makes any difference, or if we were able to do a good job of aligning it with XY mode. Okay, let's see if we can do this. I have it set to left only on the signal generator, and I'm going to go to what I believe is the left adjustment. You have like your left and right output adjustments on this thing. And we're not going by the procedure, by the way, we're just playing around. And if we see, look at that. And that pot's dirty. It needs cleaned. Needs to be cleaned. That's pretty good. And then let's go to right only and see if we can straighten it out. And we're going to go into the right adjustment. And that looks good. And let's go back and forth now. Left, right. Now, let's go back and look at our channels individually. And let's see here. Chop. And let's move them. Here we go. So there's left, or there's right, and there's left. And look at the separation that we have now. The other channel is totally flat. So you can see doing the adjustment with XY mode is pretty good. I mean, really nice. So after doing a little further investigation, I noticed that these capacitors, these little blue Nichicons, were all bad. And the rest of the receiver, believe it or not, the caps are in good condition, but they're different capacitors. This is obviously a board that Scott must have had somebody else manufacture for them somewhere along their production line. It's not shown in any of the schematics. I even looked at like the model 388 and the 380 and the 340. I went back and forth. Everything made in that era, and nowhere do they list this board. These are kind of like the little Japanese transistor radio transformers that you would see, as opposed to these big aluminum cans that should be on the original board that came with these, that's in the service manual. So it is kind of, you know, back to this again, you can see those are more traditional looking, you know, 1960s style transformers. We don't have that here. And all of these little blue Nichicon capacitors were bad. They're reading almost double their capacitance. One of these germanium diodes was bad. All the rest of them on there was good. But what I ended up doing is I ended up replacing the electrolytic capacitors. I had to. And I replaced actually five of these little germanium diodes. But the ones up here at the very end, they're all good, so I left them in there. They're fine. And I was able to get this thing to work. And again, I'm not sure if I'm perfectly aligning it how it should be, because once again, this has that extra transistor on here. If you look on the schematic, the original circuit had 4 transistors, and this one obviously has 5. So you see 1, 2, 3, 4, and 5. And they're very special. They're special transistors. I don't mean special in that you can't get them, but one of them is very, very low gain, only like a HFE of around 50. The other ones are higher gain, and they're high frequency, low noise. So, and they're good transistors, so I'm not going to replace them. And I was able to get this thing to work. What I also noticed was I don't know how strong of a signal I'm getting out of the IF section and the RF front end. This tuner is very, very finicky. You can tune it right on, but it's very touchy. I may have to clean, it looks like I'm going to have to clean the rotor on this tuner to get it to be a little more accurate. That's an easy thing to fix. You've seen me do that on other videos. But let's connect the scope up to the test point. What they have you do is there's this little wire. If I show you, it's sticking up right here. This is actually a test point. And this is where you can actually see the 38 kilohertz being, you know, from your frequency doubler, from your 19 kilohertz pilot tone. Let's get some things turned on here. I'll be right back. Okay, we're connected on here, and I have a relatively strong signal, and that's one of the things in order for this to work. I have a relatively strong signal that I'm feeding into the receiver. I'm tuning into it, and as you can see over here, maybe turn the intensity up a little bit, I do have an output on right and left, and I can go left or right and left. I have pretty good separation there. And if we look down at the scope, and this is a new scope I'm trying out because I'm looking for a little scope I can throw in my little carry bag if I'm just looking to capture a quick pulse on an X-ray machine that's, you know, if I'm not looking to do alignment, but I'm just looking for a waveform. This looks like it might be a pretty good scope. It's all touchscreen. It's only about 150, 160 bucks from Amazon. And the only negative thing I see about it is, you see here your trigger. This is your trigger level and your trigger position. If you go beyond 10 milliseconds per division, so I'll just do this for a second. You can see at 10 milliseconds, this is still here. If I go to 20, the trigger disappears. If I go back to 10, the trigger comes back. And it's just a, I don't know, an anomaly of this scope. And it seems like all of these cheap Chinese scopes, these little handheld things, they all have that same problem with the trigger. You cannot trigger or have an adjustable trigger at anything longer time based than 10 milliseconds per division. So if any of you are looking to buy one of these, and again, this is supposedly a 1 gigasample per second, 100 megahertz dual channel scope. And so far, I'm very pleased with it. It's awesome. other than that trigger issue. And the trigger issue probably won't give you much trouble unless you're trying to capture a single pulse like I have to do with it. So as long as I'm not setting it below that or above that 10 milliseconds per division, I'll be all right. But anyway, back to this. So you can see this is your 38 kilohertz, and they have you peak it with these two green trimmers here. So you have this can and this can, and I marked where they were before I started and where I ended up, and they were almost perfectly. This one was a wee little bit off clockwise. This one was spot on. This one here was a little bit off. You can see where it's zeroed out. Although we're going to check this one again. But you can see it works. It's just not very sensitive. You have to have a really strong carrier signal for the stereo to work. And I'm not sure if that's just the way this thing was, or if it's, because it's really good on mono. It's a pretty sensitive receiver. And I haven't had to touch anything in the alignment. I looked at it and it's right on with what the instructions say. But it's just this goofy multiplex, and unfortunately I can't, without proper alignment instructions, it's kind of hard to know if I'm doing this correctly or not, even though everything's very close in design. So let's check our null point with this red can up here, and then I think that's going to be good enough. So the first thing I'm going to do here is show you Exhibit A. I'll put this on here, and you can pause the camera and kind of read it over a little bit, what they're trying to say. I'll just move it around here so you can see it. Just pause the camera. So essentially, they're not really being very clear. For instance, for doing the IF alignment, they tell you to put a 10 microvolt signal, and you align the peak front end for max output. They don't really tell you which cans you adjust or in what order, but they just say align them. And you see they have you do a little hum check. And prior to this, by the way, they have you do the front end, which is the RF section. And they do tell you which ones of these adjustments to adjust. And they do give you a signal. All of this was pretty close. It wasn't perfect, but it wasn't bad. I was able to bring it in. Really didn't have to adjust it at all, really. It looked good. And back to this again, they really don't tell you how to do the IF. They just tell you to align and peak the front end, and then align the IFs for max audio. That's it. Now, the next thing they want you to do is they want you to connect the oscilloscope to that test point, and they want you to use these two green trimmers to peak them as much as you can using the waveform. And since this jumps around is like this, then they have you, once you get it close, you then take a volt ohm meter, and they want 20,000 ohm per volt ohm meter, not a VTVM. And you connect it across this little 2.2K resistor. I don't even know if you can see it in there. Hopefully you can see that. And then they have you peak it one last time. Let's see if I can get everything on the screen here. So they have you go in and you do one more time, you peak it, and you can see how I have it peaked. And then you peak this other one. So the two green transformers right there. And then you go to this red transformer. They say nothing about the black transformer, and it's actually, that black coil is right here, which is the low input oscillator here, or the low what do they call this? LV 015PC is what it is, but all it is an adjustable coil. But they don't tell you what to do with it. But they tell you to go to this red one and adjust it for a dip. So you go like that, and you see how it dips. I'll get you closer. So there's the dip, and it's going back up, so we want to get it right there in the trough. And according to them, that's the alignment. Now after you do that, you should be able to get a pilot tone, and if you don't get your pilot, then you adjust this little potentiometer, which was maxed out when I opened this receiver up. And I could see why, because it was, you don't really get stereo unless you have a really strong signal. And then if you look up in here, there's two pots, and those are your stereo separation pots for right and left. So you'd go to right stereo and you'd adjust the one, and then you go to left stereo and adjust the other. All right, where were we now? It's been weeks that I've been working on this on and off because I've been away so much for work. So I apologize that this is taking so long, and really I want to wrap this little project up. This is just a small receiver that is in my personal collection, and I have quite a few other things I'd like to get to. So I'm going to try to wrap this up. The tuner is working fairly well in mono, but still in multiplex. The multiplex is fantastic when it works, but I need way too strong of a signal to get it to trigger. And I'm pretty sure that it's not a faulty component, but it might be, I don't know, maybe. But what I did notice is on the RF front end of the tuner itself, this socket where this JFET is connected, and that is the main input there from the, here's your FM antenna coming into this coil. This is your first RF amplifier, and that socket right there, the pins of the socket itself are not bad from what I can see, but underneath where the socket connects, something seems to be loose in there. And really, without totally disassembling this tuner assembly, taking it out and servicing it, I'm not going to be able to fix that part of it. It is aligned and it is working very well, but if you jiggle that socket around, it kind of will drift a little bit. So that's something for a future project that I'm going to finish up now that I know what it is. Now what I'm going to do before I close out the video here, we're obviously going to clean up the case and refinish it and so forth. Again, I don't know if I'll get to that in this video, but I'll show you it when it's done in a future video. But what I will do is I want to go over a couple of little capacitor questions, because you know we get a lot of comments about this. Number one, about the coupling capacitors for the speakers. And by the way, I replaced these fuses with the correct ones. I have the correct ones here, these 2 amp. And I took those 14 amp monster fuses out of there. So this is a good thing. But the main thing I want to look at is we're going to talk about these first, and then we're going to do an experiment with this 1000 microfarad filter, the main filter capacitor on the power supply. So first of all, I want to show you a little chart that I made up, and let's back the camera out some so we can see it. And this is just something I printed out and took a couple notes on. And in the service manual for this receiver, when they talk about the frequency response curve, and what they're saying is that the response curve is flat from somewhere around 30 to 40 hertz up to somewhere around 18 kilohertz. And then it tails off at the ends. And they're saying that at 20 hertz, you will be 3 dB down from the level part of your response curve, and at 20 kilohertz you'll be 3 dB down. Now what does that mean, 3 dB down? 3 dB down is a term that we use when the signal is 3 decibels lower than its reference. And really, it's just a fancy term meaning the signal amplitude is half of what it was. So when you have half of the, so in other words, if you have 2 volts of signal amplitude at your reference point, 3 dB down would be 1 volt, or half of that 3 volts. So that's really all they're talking about. Because really the way the amplifier works is it's not an avalanche like a squared off thing, but as you move the frequency more and more out of that operating range, it tapers off at a certain slope, okay? And without getting into much more detail, that's really all they're talking about. So what they're saying is this amplifier, when working properly, 20 hertz should be about half the amplitude of, for instance, 1 kilohertz, where it's nice and flat response. So we're going to look at that. And I've seen many comments, not even comments, I've seen a lot of postings on forums about increasing the value of these output capacitors, and especially so that they could handle low frequencies better, and also so they could handle low frequencies at a lower impedance, like connecting a 4 ohm speaker instead of 8 ohm. What I'm going to try to show you here is just how much you would have to change this capacitor to make a small difference. So here's our chart, and this hopefully will put it into a little better perspective. So you can see right here is your level, you know, your frequency curve, your response curve, and what they're showing right here is this frequency, which we're calling FC for cutoff frequency, is your minus 3 dB point. So that would mean if you have 10 watts going into your speaker, you would have 5 watts at your minus 3 dB point. And here's a little schematic. So here would be that 1000 microfarad capacitor. Here's your 8 ohm speaker. If you do the math, here's the formula. It turns out that with a 1000 microfarad capacitor, you have your cutoff frequency, so that would be this point here, is going to be 20 hertz. Now, we can increase that value a little bit, or actually a lot. You would have to double it for that to go down. So if we use a 2000 microfarad capacitor, so we take 2 times pi times our 8 ohm resistor times 0.002 for 2000 microfarads, because that's 0.002 farads. And then you do the inverse of that, and you can see that comes right out to 9.9 hertz. So essentially you would have to double this capacitance in order to get the 3 dB down point to be 10 hertz instead of 20. But what's going to happen if we do that is you're not going to really hear a whole lot of audible difference, but you are going to expend more power from your power supply into that load down there, because now your 20 hertz is going to be higher power than it is. Now, as for this 1000 microfarad filter cap, there's a couple things going on with this. Number one, the cap is in perfect condition. There's nothing wrong with it. It is low ESR, and it's the correct capacitance, and it's working just as it did when it was new. So we could leave that in there. Now, what I will say about this is, do we know if this is the correct value? Okay. A lot of people like to increase the capacitance on the first filter capacitor of a transistor amplifier like this, thinking that it will sound better or that it will have better dynamic power, meaning when there's like a bass drum kick or something, the bigger storage of the capacitor will handle it. And to a degree, I agree with that. But on the other hand, it's not really fixing the original problem. For the short term, yes, it may make a little difference, but the capacitor is only as good as the transformer that's feeding it. So if your transformer does not have the current capacity to be able to deliver the current to the capacitor to keep it topped off, all the capacitor is going to do over time is just discharge. You're going to get ahead of it, especially when you're running the amplifier at very high volumes. So they very much work together with one another. Now, that said, if this capacitor has been undersized for the transformer that we have and for the circuit that we're using, then we're going to see the power supply sag more than it should. And in that case, increasing the capacitance a little bit will make a little bit of a difference. So we're going to check all that. Okay, as you can see, I have two oscilloscopes set up here. The little tablet scope is looking at the DC ripple on the power supply. And let me add one more channel to that. Hold on. Okay, now looking at this blue line represents the DC level of the power supply. So here's our marker for channel 2, and it's 10 volts per division. So we have 10, 20, 30, 40, 50. You have about 53 volts there, and it's pretty stable. You can see it. And then the coupling is set to AC, and I have the sensitivity to 1 volt per division, and you can see the ripple right there. So you have about 1 volt peak to peak of ripple with the amplifier in standby. In other words, no signal is being fed through the amplifier. And what we're going to do is back here, we're going to look at the speaker load across the dummy load, and these two lines down here at the bottom are going to rise up, and they show the wattage, and each graticule shows 10 watts. So if this is an 18 watt amp, you're going to get about 1.8 graticules, if that makes sense. So let's turn this up. We have a 1 kilohertz signal. And let me increase this so we can see it. And you can see the power supply over here. And as we increase power, we can see the ripple goes up, and that's what it does, and the power supply begins to sag. But if you notice, the signal still looks just fine. And watch what's going to happen here as we go up. Now you see this little flip-flop up here at the top as we go up in volume. Now it's really doing it. Now you're seeing the influence of the ripple of the power supply on the rails. And you can see how big the ripple has gotten, and you can even see a really big ripple. This power supply is rippling at almost 10 volts peak to peak of ripple. Okay, and that's when you're running the amp at high volume, and of course you're going to be getting quite a bit of distortion at that point. So now, that's with a 1000 microfarad capacitor. Now what I have here is I have a 4700 microfarad cap, and I'm going to put it in parallel with the main filter cap, which is going to make your capacitor on your power supply, which is this fellow right here. It's going to make that from 1000 microfarads to 5700 microfarads. So let's clip that on here. Let me turn a light on for a minute. And I'm going to clip this right on to the other capacitor. I'm going to turn it on. And you can see right away that it has reduced the ripple on the power supply. And my trigger point is set kind of low here, so I'm going to lower it so that you can hear. All right. Now watch as I go up in volume. Now let's see what this all does. All right. Here we go. And you can see the ripple starts to go up. And now we're at about over 20 watts per channel, and it's starting to clip off at the bottom end and the top end just a little bit. You're getting a little bit of that warbling, but the transformer is actually handling that extra energy. So what that means is this amplifier will benefit from an upgrade in your main capacitor. All right, we now have, what is this? An 11,000 microfarad capacitor at 75 volts, because we're at about 51 or 52 volts. I have a 50 volt 10,000, but I'm kind of pushing that one. That's another thing. These old capacitors, when they were rated at 50 volts, for instance, you could go above that a little bit all day long and they would work. Modern capacitors, when you look at the rating of them, they are physically rated for that voltage maximum, and if you exceed it even by 1 or 2 volts, you can damage the cap, or at least severely reduce the life expectancy of the cap. This 4700 I was using was rated at 63 volts, so it was more than adequate. But okay, let's look at this 11,000. And you can see once that cap charges up, there is no ripple. So let's turn the volume up and see what it does. You can see the ripple looks kind of funny now, doesn't it? And as we increase, we get a little more power, not a whole lot, but we get about 2 more watts of clean power out of this. But you can see it's still warbling around. So it helps a little bit. And let's just compare this. If I take the capacitor off, I disconnect this one, and you can see the ripple comes back. Let's just see what that does, how that affects. And you can see just a little bit sooner this starts clipping off, but it really doesn't make a big difference, does it? You're not seeing what I'm there. I'm sorry. So you can see it's really not making that big of a difference, even though we're getting crazy, ridiculous ripple on the power supply. You can see there, it's not really making much difference on the amplifier itself. Let's connect this back up. Just like that. And here we go. So you can see right there, and you can see this is jumping around a little bit because we're getting near the rail voltage. You can see our ripple is kind of strange looking, but it has reduced, and this is from your transformer not being able to keep up now. Just like I said. And if I disconnect this while we're running, you see you get that little bit of flat top up there. So it makes a small difference, but it doesn't make a huge difference. When the thing is at maximum volume, you could make an argument that it makes a slight difference in the power of the amplifier, but when this thing is running at normal listening volumes below its maximum rating, it makes very, very little difference. So yes, we could put a bigger capacitor in there. It would reduce the ripple, but I highly doubt that it would make any difference in the sound, and it would make a very small difference in the maximum power the amplifier can produce. I hope that explains that part. And the other thing is, if you notice, this is kind of jumping around, and if I disconnect this 11,000 microfarad cap, it stabilizes. That is because of the resistance of these alligator clip leads going between the two capacitors, because that other capacitor is directly connected to the transformer leads, and these are actually connecting through these wires which have resistance. So you have a difference. You actually are getting a ground loop between, a voltage differential, or a common mode signal, we could call it, between this capacitor and the capacitor in there. And that's what you're seeing there. If this was directly connected in there, you wouldn't have that. So the moral of the story is that the folks that designed this thing knew what the heck they were doing. And when you start just trying to replace one component, thinking that it's going to make a huge difference on the performance of an amplifier, or any circuit for that matter, usually you will not get the results you expect, because these were very specifically designed the way they are. And when you change one thing, it affects other things that you will also have to change in order to get it to work. Not meaning that you can't do that, but usually just changing a capacitor with a different value won't fix the issue. Won't hurt it, but it won't make the improvement that you might expect it to. So I'm going to wrap this video up right here, and I promise when I do the case replacement, restore it and get this thing put back together, I'll show it to you. Where are we leaving this? Well, everything's aligned, everything's working. It really didn't need a whole lot done to it, as you saw. The tuner was the biggest issue, and it really specifically was the multiplex. And after rebuilding it, we found all the electrolytic capacitors in the multiplex were bad, so we had to replace those. And one of the germanium diodes was bad, we had to replace that. We had a bad Zener diode and one bad capacitor in the power supply board, so we replaced that. And now all of our voltages are where they should be. And last but not least that I found was that this socket has a loose connection inside where I just don't have the time at this point to tear it all apart to fix it. But that's not a big problem, because that's just a mechanical thing that we can resolder or fix later on, and it should be good. So this receiver is pretty much good to go. And once I clean up the case and refinish it and put it together, it'll be a nice thing to sit, put somewhere and listen to it. It has a very nice sound to it. And oh, I forgot to show you guys the 3 dB down, didn't I? Let's do that real quick, and then I'll wrap up the video. Okay, I have a 10 kilohertz signal being fed into the amplifier, and we are just setting it to 4 gradicules peak to peak, just to have a reference point. And if I go to 1 kilohertz, it should stay pretty flat. I have to go back and reset this. And you can see it does, 4 gradicules. And if I go down to 100 hertz, it's still right there on 4 gradicules. And if I go to 40 hertz, it's down a little bit, as we can see. And if I go down to 20 hertz, it's down even further. And it's actually a little better than 3D, it's a little higher than 3 dB down. So it's actually performing better than the specifications are saying. And if I go to 20 kilohertz, it should be about the same as the 20 hertz. And you can see it is pretty close. We can see we're getting a little bit of phase shift between the 2 channels. No big deal. And then if I go down to 15 hertz, it's going to really drop. No, it's actually, yeah, it's dropped, but it's still not all the way down there. And if I go to 10 hertz, there you go. Now, let's try something else. Let's switch our impedance. I'm going to go back to 1 kilohertz. And let's switch our impedance now to 4 ohms. So now we're driving 4 ohms into here, and this amp's going to start getting hot now. There's 1 kilohertz. Let's drop right down to 20 hertz. And you can see at 20 hertz, we're already starting to get some distortion in there, and it is getting very close to that 3 dB down. Not quite, but it's almost there. So, and as the amp heats up, you can see it's got some weird looking oscillation going on there. It doesn't like the 4 ohms as much. So, there you have it. That kind of shows the frequency response curve on that a little bit, but it's actually outperforming what it said it could do. So here's 1 kilohertz again. So I don't know. I think those 1,000 microfarad capacitors there on the speakers are working pretty well. Okay, this is not going to be one of my best videos in closing because it was done over such a long period of time, and I really don't know how many, if I repeated myself, there's a lot of things I'll have to go through and kind of stitch this all together and make some sense of it, huh? But anyway, that's going to be a wrap on this. I will show you the case and everything, like I said, when we get it done. And until next time, and we have to replace this meter too. The coil's open on it. But until next time, I wish you all peace, joy, happiness, and good health in your lives. And I hope you're all well. I know I haven't released a video in a couple weeks. It's going to be crazy for the next month or two with work. But hopefully we'll get some time on the bench here and I can get some fun videos out. Anyway, until next time, stay well, and we'll see you again soon. Take care. Bye-bye.